I think to me, like, the biggest question is how do people get proper, as I say, problem distributions? Because that then makes it a very useful input, can be used for any probabilistic method. Right now, it's a bit of tricky thing, which input you trust to go.
So we'll start the second half of the talk, and maybe we'll go on till 6:50.
No, not till 6, I think. Let's not wait so much. So thank you all for staying back. You must have done something good. My first session that you're still here. So I think now we'll just start talking about the kinds of things that normal people, or let's say people on the street, would call causality. Right? So far I was talking about causal graphs, and that's a very technical kind of abstraction that's used. But let's take a motivating example, again from health. This is actually some medical record of a patient. And if you look at this, what's possible today is that you may use NLP or BERT-like models to say, what issues is the gentleman suffering from? So this doctor writes, this gentleman has multiple issues, tinnitus is one of them. Models can extract. What procedure did he go through? Sure, there's a sentence here which mentions what procedure did he go through. But what's not possible is to ask, what is the likely diagnosis? Because now you're entering the territory of doctors, right? When doctors read these things and other doctors would ask and answer, oh, this looks like this is the likely diagnosis. And they can also give a reason why that is the case. What tests would you recommend given this history? Right? Obviously, NLP models are not good at that. And then you can also ask kind of counterfactual or future questions of, oh, if the blood sugar test returns 200, how will your diagnosis change? These are kinds of questions that doctors ask other doctors, actually, and how junior doctors get trained. So there's a book out now, which is from Peter Lee from Microsoft and a couple of medical researchers. They did exactly this, but then they gave it to GPT-4. So this is one of the examples. I think this is some patient. Actually, before the patients, let's look at one example they tried, which was like our first talk, right? So here they're finding that white blood count levels are lower of people who are tested at 5 to 6 a.m. And they're trying to ask the LLM, what do you think accounts for this difference? So this one, the LLM is very easy. We've shown it multiple times now. It gets it right. It says that, look, the timing of the blood pressure measurement is suspect. If you're getting it done as early, then that means there must have been something serious, and that's why you have to rush to the hospital. And so it kind of can easily get these kinds of domain knowledge. By this time, you should not be surprised by that. But this is surprising. So this is an actual history of an anonymized patient. It's some girl who was brought to the emergency department. She had some respiratory infection, other problems as well. And the question is, what is most likely to be a normal patient and why? And they asked the LLM this question, and the LLM is able to answer what's the right option, and as well as give some explanation. I think you and I won't understand this, but the doctors in this book say that this is the right explanation as well. So now it's kind of doing something more, right? It's not just telling you A causes B. It's showing two capabilities. First, it can understand concepts from text, because we did not even ask it a specified thing like here's A, here's B, tell me what's going on. We just gave it a paragraph. Right? So first, it can understand concepts. And second, it's able to do some kind of causal reasoning over there. So we again thought, how can we study this systematically? If people who are in medicine are saying that this is something special, then can we actually take their anecdotes and run with them and do this systematically? And so before I show you the results, just a little bit of prelude to what we'll discuss. This is a different kind of causality. So far, we were discussing type causality, which is what is usually used in science. This is about variables and their expected effects on a population. So you might ask, does smoking cause lung cancer? Actual causality or event causality, which is, for example, what doctors do, is reasoning about a single event or a single patient. So here you might ask, Bob, who's an employee of a coal plant, has been smoking cigarettes for 1 year. Did his smoking cause blood cancer? The only difference is you're asking about a very specific event that happened. And so there are other examples as well. A doctor washes their hand before surgery. What would have happened if they did not wash their hands? So here, remember, you're not concerned about what's the impact of washing hands. You're not WHO. Right? You're not trying to issue guidelines. You're just caring about this doctor and thinking about what is the effect of them washing their hands. And just like causal discovery. Yeah.
Traditional causality without LLM cannot make conclusions based on single event.
That's what I will come to the next slide. Yeah. So usually traditional causality or event causality has been very hard to formalize because it needs a causal frame. And by causal frame, I just mean what factors are relevant to this question. This is a very good example for you to think about what I mean by that. So in fact, this is an example in a benchmark that we'll use as well. So there's a story of Alice catching a ball, and the next thing on the ball specifically was a solid brick wall, and then there was a window. So you can ask as a normal human being, what caused the window to be intact? And if you're a machine, there are so many answers you can give, right? You can say gravity. You can say Newton's laws of motion, like it was stopped and it was following some laws, and that's why it did not hit the window. You could even say the Big Bang. All of those are valid in some world based on how big you want to create causal graph. But obviously, for the right answer for most people would be Alice's action. Most people would say that everything else remaining constant, it was really just the Alice's action that prevented the window, not Newton's law. And so this is so easy for us, but I think it's very hard for machines. And that's what, Rahul, is the answer to your question. Like people in traditional causality were not even looking at questions like these because it was just so hard even to decide what variables should I put in my graph before I start analyzing this problem. And obviously, like depending on which variables you input in the graph, your answer may also change. It depends. You think of necessary or sufficiency? So there are two ways of looking at it. We'll come to it. What you're saying is the necessary definition. Even if it did not have did it, it would not have happened. But think of the sufficiency definition. Every time Alice catches the ball, the window is safe. So in that way, it is a cause. And what you're saying, actually, let's come to the next slide, right? This is also a point of contention in this literature. Is exactly what is the right definition of causality in a problem. And so usually there are three steps. The first step is determining the causal frame, like Alice's action, wall hits wall, wall hits window. This was very hard before. Like people would just not even try it using machine learning. They would just use humans to do this. The second thing is what you just asked. I mean, there's a lot of debate even today on what is the right definition. Is it like necessary, which means if Alice had not acted, would the window still have been intact? Or is it sufficient? If Alice acted, would the window always be intact, irrespective of whether there's a wall or not? And then finally, the third one is well studied. I think the third one is kind of like the estimation of the STM in causal graphs. That's a well-studied problem. A lot of literature on that. If you can get 1 and 2. In fix 1 and 2, 3, we still have a lot of tools. And what we see, of course, is that LLMs are good at one. They're good at taking a question like this and answering reasonably about necessary causes as well as sufficient causes. And I think what's even more surprising here is that there is not even a baseline for this method. Like there's no algorithm that people have tried to answer these questions just because they thought it's so vague. Like how will you even attempt it? So what I'll do is just to whet your appetite, we'll go through a building block. It's a much simpler task compared to necessary and sufficiency. It's still counterfactual reasoning. It's not simple, but compared to necessary and sufficiency cause, it's a simple task. So we'll talk about that first. It's also good because there are NLP benchmarks for this task, and then we'll go to the main.
Have been attached to, I mean, LLMs do it, but prior to this, could you not address it to logic?
Yes. So that's step 3. So there are a lot of methods actually. Joe Halpern has done so much work in this step 3, which uses logic to infer the answer. But before that, you still have to decide what is the causal frame, right? Like, is Alice's action also something that can be changed? Is the location important to be known? Like, are you in space or are you on Earth? We didn't mention any of that, by the way, right?
Yeah. So I would separate the problem into, I mean, I don't know whether you could separate the problem into 2 parts. One is understanding the causal frame from the language.
Yes.
The second is understanding given the variables, what are the...
Yes, see, that's 1 and 3, right? Exactly. Yeah. So 3 is done. I mean, 3 you have great literature. 1 was not done, and that's why people did not even use 3 in practice. Just the same issue again. And what we find is that LLMs do 1. They're not good at 3. No, I don't think they're good at logic, but they're good at just getting the causal frame. So yeah, let's start with counterfactual reasoning. It's a very essential element of any agent if it has to reason causally. It can basically try to imagine worlds where something has changed and then give you an answer on what would have happened in that world. It's very closely connected to necessary cause, because the necessary cause can also be thought of as what if this event or this action did not happen? Would the outcome still have occurred? So luckily, there was a data set available for this task. It's called the CRAS counterfactual reasoning benchmark. And people manually collected 275 questions, which checked whether NLP models can imagine about different scenarios. So one question could be a doctor washes their hand at work, and what would have happened if they did not wash their hands? The right answer is A, patients could get an infection. But to do that, you have to kind of understand the relationship between washing hands and infection. And if you think like an NLP expert, it's quite hard because the question has nothing to do with infection. So now I have to learn that from other sources. Another question could be an oil tanker sails across the ocean. What would have happened if it had broken down? You need to know oil tankers, ocean, and environmental pollution. They are connected. That if you know that, then you can give an answer. So what we did was just ask exactly these questions. So in this part, we did not do any prompt engineering. We asked exactly this question to the LLM. And what we find is previous work was showing GPT-3 had about 58% accuracy. Models based on T0, which is an encoder-based model from Google, had about 72. Human annotators have about 98% accuracy. And GPT-4 today is about 93 or 92% accuracy. So it's almost at the level close to what humans can do on this task. And again, it's not perfect, right? So I'll show you an example. In this case, the LLM got the answer wrong. But if you look at its answer, you might even think that it was actually better than the benchmark. So the benchmark says that he would have got wet. If a person catches a water balloon, obviously they'll get wet. GPT-4 goes into some long essay, but ultimately it's saying that either B or D can happen, depending on whether the balloon bursts or not. If you really catch it well, then it won't get wet. Now again, you can think about how it's able to do it. I don't know, but it is able to get these kinds of answers, and this is now evidence that it's not memorized. Because if it had memorized this data set, which is publicly available, it would have learned the right answer, right? What would it need to do this kind of complex reasoning to both support B and D? And then I can also do stupid stuff, right? So here we ask, the man walks on the street. What would have happened if a man walked on a bed? Nothing would happen, right? I mean, he can walk on a bed, but the model kind of thinks about, oh, this person is walking on a bed, and a bed is not the fastest way of transport, so they will get late. And so that was just to show that these models also have some capability to imagine things and then at least give you some kinds of plausible answers. And again, I like this quote. I don't know who said it, but basically you can think of like one man's hallucination is another man's creativity. So if you're writing a movie script, you might think this is very creative. I might have a bread that walks. But of course, if for most purposes, you can think of this as hallucination. It's not a good answer.
The conference sort of thing made this sense like the fact that it's giving such detailed answers, that it provides some way to like have an input for those logical deduction methods.
I don't know how. I think the logical deduction also depend on premises and their probability. Those are the only two inputs they take.
It's not just like predicted that first order logic. So it does require some probabilities
Yeah. So Alphan's framework, think of it like you need to give a graph and the equations. So you need to give the SCM. And then it does all kinds of logical. So let's come to our main task. So necessary causality would be if event C does not occur, then the outcome should also not occur. And if an event occurs, then the outcome should not. And sufficiency means if the event occurs, whatever else happens, the outcome will also occur. And in general, sufficiency is harder because sufficiency more requires the causal inference. With necessity, you can still get away by just changing one variable. And so here it was very hard because there's really no data set. It's a new task. But what we did have were textbooks on this topic from Pearl, Joe Halpern, and other people who had just painstakingly reduced the problem to some 7 or 8 types of issues or types of problems that can come up, and where models still have a lot of difficulty in getting the right answer. So I'll talk about some of them. So one is called symmetric overdetermination, where you give some outcome where 2 causes simultaneously have caused somehow. I'll give examples of this. Another hard thing could be like there's a switch, like there is an action that should have caused the outcome, but in the middle you change something, and because of that, the action was irrelevant. There are many others. There's early preemption, like you try to do something for that outcome, but someone else comes in and sort of reduces your impact, and it goes on, right? So people in the literature had painstakingly collected hard examples of where it's very tricky to find necessary or sufficient causes. What we did was we just took all of those examples. There are not many, there are only 15 of them, and said that this is our test set. We'll just put LLMs through this kind of setting and check whether they can recover the necessary or sufficient cause. So overdetermination has a nice example where Alice and Bob are firing a bullet at a window. They simultaneously strike. So the right answer is that both are sufficient, but none of them is necessary. Because it doesn't matter. Even if one of them did not shoot, the other person would always have shot. What's a nice example? Early preemption we just discussed. So you were right that it's not necessary, but it is sufficient. And so that's what the right answer is for this example. And these can get also very philosophical or very sort of muddy. So this is a nice example. What happens is like first someone intends to put poison in someone's water, but then they did not put it. And someone else puts antidote, not poison. And then you're supposed to answer whether the first action was necessary or not. Yeah.
The previous page, if I notice all the regret types,
yeah.
So timing seems to be an important constraint for call.
That's true. That's true.
In the original Perl framework, like he somehow removes time from the concept of call. He suggests instead things like interventions and through.
Yeah, because that's the difference, right? He's talking about type causality or general causality. That's more like smoking causing lung cancer. So for those concepts, you can just get the conditional distribution or interventions. Here it's one person, like one person's life when you're talking about what happened. And that's why time is so important, because it's a chain of events that lead to the outcome.
Okay, let me rephrase this. So if you speak about, let's say, mathematical statement, A causes B causes C, then the concept of time may not need to occur. And yet all of these seem to. So is this, so what I'm asking is, are these a subset of all the beginnings that can?
Yeah, they're definitely a subset. Yeah, they're not exhaustive. They are more like examples that we could get from the literature. They're not exhaustive. Just trying to think if there is an example without time. I think here it's hard. I mean, think about it. Like if you have only one outcome, then all the causes have to be before it. Right? And if you're trying to explain some failure, let's say, let's move to a different thing, right? You have an internet system, something failed. What happened? Most likely there are things that happen just before.
And humans ourselves, use time as a.
Yes. But there's nothing necessary about that. You can also have scenarios without. Yeah, so I think these are kind of interesting, right? These are examples which are trained to be hard for algorithms. And so we thought, okay, let's just try GPT models on that. So here, I think we did something interesting. I think perhaps you were asking this. The first time we tried LLMs, they failed. I was trying GPT-3, it failed. And it was not even getting the basic things right. So what I did was there's some literature saying that you can ask the LLM to generate a prompt. Sometimes that works better. So what I did was I gave some of these examples. There's a little bit of cheating, you can say I did. With some of these training examples, like or variants of them, I just gave it to another instance of an LLM and said, this is the input, this is the output, necessary yes, sufficient no. And I gave a couple of them and asked the LLM, can you tell me what task this is possibly about? So there are some examples of this task. Can you tell me what the task is? And that's how we got these two strings. Essentially, the first necessary calls, the LLM, for whatever reason, thinks of it as a minimal change principle. And the sufficient calls, it thinks of it as a multiple sufficient causes principle. When I searched for it, I found that this is what philosophers or other literature calls these things. And so that's what we do finally in the prompt. So what we ask is that you are an expert in counterfactual reasoning, and you have to use either of those two principles. So either we ask you to use the necessary principle, which is minimal change, or we ask you to use the sufficient principle, and then we just get the exact prompt. So GPT 3.5 still fails. As you can see, its accuracy is about 50%. But GPT 4 somehow is getting 86%. This is all, again, very mysterious. What this is showing is that definitely with model size, things improve. But it's also showing that this task is much harder than graph discovery. Because graph discovery, GPT 3.5 could easily do. Here, it completely fails. And so here's an example. Again, not so much to read into it, except that, I mean, based on what you ask, it also gives you a reasoning, just like a person would, about why it's saying that it's a necessary cause or sufficient cause. And by the way, it can also give you the right reasoning and the wrong answer. All those kinds of things still happen. What's surprising is just that they often happen less frequently. And so you still can get 86% accuracy on this task. But if you read some of the other 14%, you might think that this model is complete garbage. No one should use it. So that's the trade-off. And so errors are actually unpredictable, and LLMs can get confused. Yeah.
What are the processing things corresponding to I noticed one of the short circuits can
cross means so there are not many, there are 15 examples. This is the description of the experiment. Tick means you got the right answer. Cross means you got the wrong answer. And so again, the question came up, right? I mean, these are very popular examples in textbooks. So the LLM must have memorized them. So then we created our own data set. So this was a bit of a fun experiment where we just changed all those examples and took them to the world of chemistry. Reagents, fires, and all kinds of fun things happening. And so now, if you remember, the old convention example was just like people are shooting at some target. We just changed it to something like there's a fire in the chemistry lab. Can of water would douse the fire. Agent X and Y both spray a can of water. Dousing the fire. So there is some pattern that still matches, but we tried as much as possible to make the language very different from those tasks. And surprisingly, accuracy was slightly higher. Again, GPT-3 fails, but GPT-4 was able to somehow get some high accuracy. Again, some evidence that it's not just memorization. It's some non-trivial stuff that it's doing, that it's able to, and think about it, right? I mean, this is a harder task than what the logical problems solve. So the logical problems assume that the variables are already given to you. You're just doing the logical conclusion using those variables. Here, a single model is doing both. First, it's discovering the variables that matter. Then it's also answering your question using pseudo logic and able to get high accuracy. So a couple of takeaways, right? So one is that there's substantial improvements in LLM's counterfactual ability. And this is so close to human level that you can almost imagine deploying these kinds of systems in, let's say, factories. In factories, you have these IoT systems where a lot of things are connected. You might ask, this branch of the factory has failed, this kind of motor has failed. Why has it happened? Right? I mean, these models are so good that you can actually deploy them in these kinds of scenarios and get reasonable answers. Of course, connected with some kind of data algorithm as well. But they are now very close to real accuracy. And in practice, I think what is important is, because people have tried this, right? This is not a new idea. What would happen is the system would work well for what it's trained for. But if you ask it simple common sense questions, or if you ask it something very simple but not from the data, it would not answer it. And so that's why those systems didn't succeed in the past, but now it feels like they may succeed. And of course, they fail as well. So you can see the paper for additional experiments. We also tried even harder tasks. So necessity and sufficiency is one thing. You can also try to judge whether this was a responsible action or not. So basically, was the responsibility or blame should be put on this actor or not? In those, we did not get good results. Even GPT-4 only gets 70%. There's still room for improvement, but I think just this also is quite shocking. Human annotation. So I think that's where it gets tricky there, because blame is very psychological. There are interesting things where, suppose both lead to the bad action. In one case, you did something. In the other case, you chose not to do something. So people put less blame on the person who chose not to do something. So that's why I think it gets harder, those kinds of tasks. Yeah, so I think that's all of the empirical results. Maybe I spent 5 minutes on discussion, like what I think this means for causality research. So 3 things we have tried to answer. One is a very behavioral question, practical question. Can LLMs learn causal graphs? And the answer is yes. And in the future, the next couple of years, you'll see a lot of papers which try to combine traditional methods with LLMs. I mean, the performance is so good that it would almost be irrational not to attempt to work with LLMs. The second question was, can LLMs answer counterfactual queries and infer actual cause? Here, our evidence is mixed. I think only one LLM, GPT-4, can do even a reasonable job here. And also, the limits are not well understood just because the benchmarks were not good. We just had to create this 15, 16 number of examples ourselves. So here, I think there's still a lot of things to be done. But prima facie, it seems like it's enough to fool humans. That much capability they have. And then finally, I mean, this is kind of the holy grail. Like, can LLMs do causal reasoning? I think our experiments are insufficient for that. We need a lot more exploration to truly understand this question. Actually, there's one hypothesis from Willig et al., which is quite interesting, which is that it's learning correlations of causation. What it means is that on the internet text, there's a lot of things written like A causes B. And just learning A causes B is kind of learning a correlation of a causal information. So perhaps that's a very likely way of thinking about it. But then this doesn't explain the counterfactual queries and the out of distribution stuff that LLMs can do. And yeah, so I think what's new, of course, is that you can now do a lot of stuff automatically, which perhaps previously only humans could do. Inferring causal relationships as well as extracting them. What's not changed is that we still need some rigorous, well-documented steps or well-documented checks that make sure that what you get is truly causal. I think what I showed you is great for presentation, but it's not ready for use anyway. And so I think it will take time for us to make this more robust so people can actually trust it. This is my last slide. A lot of new research questions. I think in some ways, this is the kind of talk which opens more questions than answers. I think this is more about just showing some interesting results that we are seeing today. And we don't have any idea why. So many questions. One question, how do you improve causal reasoning in LLMs? First of all, how is this capability even possible? Right? What is it about sequence-to-sequence learning that makes you reason about causality? When it fails is also very important. Right now, we don't know. So it's just random for us when it fails. If someone can find out ways in which knowing when these methods fail, when database methods fail, and how to combine them, very useful. And of course, you can also think of systematizing actual causality. Like there are a lot of questions that lawyers ask, for example, right? Like a person died on the street, this car was speeding, but actually they were following the rules, and this person was not following the rules, he was jaywalking, whatever, right? So there are lots of these kinds of questions that come up in law, which talk about attribution, which talk about what was the reason, what was the necessary cause. Those kinds of data sets were not touched at all by causal research, but now it's possible. Now you can ask a lawyer to give that case document, feed it to an LLM, and then sort of start asking questions. At least for brainstorming, it's very useful. And then finally, of course, we want to go towards end-to-end causal inference, where more and more of these tasks which required human input will now require less of human input at the start. So maybe a human only verifies the graph. They don't have to actually create the graph for analysis. And with that, yes, I will stop. Any more questions I'm happy to take. I'll be here. And you can also write me questions. I think my email was on the first slide, so I'll just open it up once more. Yeah. Can reach me on these links. Thank you so much for being such a patient audience. Yeah.
Two questions on your last slide. So where you might have to go back all the way to your
okay, sure.
But, the points 3 and 4. So on the inference side and the one just before that on the legal one that you mentioned. The first one, the inference is if we are able to give some assurance or guarantee that we are correctly finding the causal graph with a particular accuracy, with a particular confidence, can that translate to causal inference with a guarantee? So is that a question that so I think there might have been some work done on the causal inference side that you have an approximate causal graph. What do you do with it?
I think there's actually less work than you would imagine, just because the community that works on causal discovery, discovering the graph, is different from the set of people who work on causal effect inference. So I think it's changing a little bit. People are now understanding that ultimately only care about the downstream task accuracy, right? Why do you care about so much of the graph, as we were discussing? But yeah, I think there are works now that are coming up. So interestingly, LLM makes it easier. I'll tell you how. So previously, you had the same data set. You used it to create a causal graph, and then also use that graph to do, let's say, effect inference, right? So now there's a dataset pollution happening because you're learning a graph from the same data. And then you're also using a learned object, a learned statistical object to estimate some other thing, right? So the p-values are very hard to estimate because now you are kind of, they're conditional on some statistical object.
Yeah. So you can do some sort of Bayesian inference over the
exactly. Yeah, you can do Bayesian inference. But in case of LLMs, you're even safer because your graph is coming from some other data, so you're not even concerned about it. So you can use it as if it's a user providing.
And then the second question was in point 3. So with regard to judgments and things like that, so in fairness literature, we keep hearing about the compass data set where there's some judgments. So that was treated earlier as a supervised learning problem where the model is simply asked to provide yes or no. But now you might be able to augment that with certain causal reasoning and ask why you said yes.
Yes, in fact, you can also augment each row with the judge's text, whatever the judge wrote as a description of it. Judges usually write a paragraph, right, or more about why they made a decision. It'd be interesting if someone augments the data set with those points and then sees if.
And then compares,
In fact, I mean, if you think about fairness also, right, that's a very good way of identifying bias. So far, we're only thinking of looking at the statistical patterns of someone's decisions. Why not also look at what they write when they make those decisions? That will often help.
I think one of Professor Barenboim's work on causal fairness analysis also like where he speaks about he doesn't use LLMs, but he speaks about variables and then how you separate the variables into
the mediation effect. Right? Yeah, yes.
Discussion on like models trained on large data versus models. So it's still on legal judgment.
Yeah.
So is this something that has been noted? Like if you're trying to say infer in causal, but the for discovery, but this like other direction. It seems like in fact specialized model versus
specialized model always performs worse. Okay, now it's a especially the LLM literature, it's a well-established empirical result, which is that even if you want the model to have one task only, it somehow helps to learn on a diverse set of experiments. I think the best example is a paper by Sebastian Bobet, where they were trying to make a model learn how to solve linear equations. You might have seen that, right? And it just turns out that training it on the entire Wikipedia improves its performance, even though the entire Wikipedia has a lot of stuff unrelated to that. So this is something people don't understand, but it's well established that even for a specialized field like law, it's better to train a model on everything and then maybe just fine tune it. Yes. Yes.
But there are some works that say GPT-4 itself is a mixture of experts.
That's how it has been trained. That's the architecture.
Which means they're on different data sets.
So as per that, a mixture of experts is like a training efficiency technique where each input is not passed through your entire network. Based on the sort of vector it has, it will choose which path in the neural network it takes. Right? So how are you thinking of that as?
And I thought each of those was trained on some part of the data. So let's say you find it
trained on everything.
Right.
I think what they're training is you could almost think of it like in a very naive way. There's like a medical GPT inside it, there's like a law GPT, and based on what you enter, the model learned which part of the.
Right. That's exactly what I'm saying. But
that's intuition. I mean, that's not what I'm saying. Is that intuition. Ultimately, it's just a training efficiency trick. It may be medical GPT, law GPT. It may also be, I don't know, American knowledge, English knowledge. People don't know what parts it's learned. Yes.
Based on the inside of the
yeah.
There is some similarity in the word moves.
Possibly, but then I think it's not doing the reverse, right? So, like, if left, let's say something in your left also causes left back pain, you can also ask the opposite question, right? Does left back pain cause that root cause? It won't. It doesn't often answer yes to both. So, yeah, I think the levels to both.
Questions. I'd like to invite Professor Siddharth to present the topic. Thanks to us.
Okay, thanks.